Hello everyone. The title of this video is Solving Compound Inequalities with the word AND. And I'm going to be going over many examples in this video. And if you would like, I would like you to before I work on it, finish an example before you watch me do it. Pause the video, try to work on it yourself. Also, in the description, I have timestamps for every single example in this video, so you can skip around a little more easily. And all these examples are taken from openstacks.org. It's a website with free online textbooks, and the particular textbook I'm looking at examples from is their Intermediate Algebra 2nd edition, and specifically section 2.6 on solving compound inequalities. So in my video here, I'm going to be going through the section Solve Compound Inequalities with the word AND as the connecting word. Right? A compound inequality is just two or more inequalities connected by a word either AND or the word OR. So example 1 is going to correspond to number 376 here, and I'm doing all the way down to example 26, which will correspond to number 4R1. So if you'd like, if you do some counting and you'd like to see work on a specific exercise here, just count down to what example that would be, and then go to that timestamp in the video. All right. Okay, so let's get started here. So again, number 1 here, this corresponds to exercise 376 from section 2.6 of the openstacks.org Intermediate Algebra 2nd edition. And in every single one of these exercises in the video today, every single one of these examples, I have the same instructions. As to solve the compound inequality, graph the solution on a number line, and write the solution in what's called interval notation. Now, I'm hoping that you know how to solve inequalities that involve either one step or multiple steps from previous videos I've put up or other experiences you've had. So I'm assuming you know how to solve inequalities. Get the variable alone on one side and a number on the other side. Now I personally prefer the left side, getting the variable alone on the left side. And also I'm assuming you know what the brackets and parentheses mean in interval notation. Right? If a bracket is above some number, is around some number, that means that number is a solution to the inequality. And if it's a parentheses, that means the number that the parentheses is around is not a solution. Again, I'm assuming that you know a little bit about interval notation. Okay, so the first compound inequality we're given is x is less than 3 and x is greater than or equal to 1. Okay, so first you solve both inequalities, which is already done here. But to work with these compound inequalities, you solve both inequalities. All right, done. And then what I'm going to do is I'm going to graph both on the same number line. Now this isn't the final graph. This is a first graph, all right, like a rough graph. So I'm going to graph both on the same number line. Let me show you what that's going to look like. All right. So here's the number line, and I'll do one above and one below. Now the first one is x is less than 3. All right, so here's 3, and I'm just marking 3 off somewhere on the number line. And x is less than 3, but not equal to 3. So those are all the numbers left of 3, but not 3 itself, which you could indicate with a parenthesis, or an open point, a hole. And then I'll graph the second inequality that's part of this compound inequality below. X is greater than or equal to 1. So all the numbers greater than 1, but not, and 1 itself. Now make sure you mark numbers in the correct places. I already marked down the number 3 here. The number 1 is less than 3, so that should be to the left of 3. Right, here's the number 1. So be careful, make sure you're marking numbers in the proper places. And then, all the numbers greater than 1 are to the right of 1, and equal to 1 as well. Now to indicate that, I can put a rectangular bracket like this, or a closed point. Alright, so I have solved both inequalities, graphed both over the same number line, and this is not the final graph. Okay, this is not the final graph. This is a rough graph. All right, I'll call it a rough graph, a first draft, if you will. We'll get the final graph lit in a second here. Now for the word and. All right, when the word and is the connecting word in a compound inequality, we're looking for numbers that satisfy both inequalities at the same time. So the solutions that will be on our final graph, right, the numbers that will be on our final graph, are numbers that satisfy both inequalities at the same time. All right. So another name for this is the intersection. So you look at the graphs that I made here, and what we're looking for are the numbers that are in the intersection of these graphs, the numbers that belong to both. So, where do they overlap, if you will? See, all these numbers to the left of 1 are in the first graph, but not the second. So they won't belong in the final graph. 1 itself belongs in the final graph. That's in the overlap. 1 is in both graphs. And then all these numbers in between 1 and 3, but not 3 itself. All right? But yeah, what we're looking for when we have these and inequalities is there any overlap, intersection in the two graphs? These numbers then will belong in my final graph. And then 3 itself is not in both, right? It's not in the first one. And then the numbers greater than 3 are not in both. They're in the second graph, but not the first graph. Okay, so noting where the overlap is, I make what I'm going to call my final graph of the compound inequality, the solutions to this compound inequality. So here's another number line, and the numbers 1 and 3 were marked off up there. And what we can see is that every number in between, right, every number in between 1 and 3 is on both graphs, is in the overlap. 1 is on both graphs. So again, to indicate that it is a solution, it is on both graphs. It satisfies both inequalities. I put the rectangular bracket, or you can put a closed point. And then 3 is not on both graphs, right? 3 is included in the second graph, but not the first one. So it's not a solution to the compound inequality, this and inequality. And if a number is not a solution, you indicate that with a parenthesis, right, or an open point. So here's the final graph. All right, not this one. This one would not be accepted by any professor, any instructor. It shouldn't be. This one will be accepted. All right. Now notice one big note here. Sometimes you can take a compound inequality and write it with the word and, right, with the word and only. Sometimes you can write a single connected inequality with like 3 parts to it. If the solutions, right, if the solutions are between, have some sort of betweenness to them like we have here. See how all the solutions except for one, all the solutions are between 1 and 3. So if the solutions are between 2 numbers, then you can, if you wish, write a connected inequality. Then you can, if you want, write what I'm calling a connected inequality. And that would be like the following. Right? Here's this connected inequality here. So all my solutions, all the values of x, right, what, the variable here was x, are between, right, so like this, less than one number, greater than another. And they're between the numbers 1 and 3, like that, right, so this is x is between 1 and 3, greater than 1, and at the same time less than 3. And we see that 1 is included in both, so I put the or equals to on the by the 1, but 3 is not included, so I don't put the or equals to there. Alright, so you can do this if you wish. Alright, but the only time you can do this, alright, people make a mistake with this quite often. The only time you can do this connected inequality business is when the solutions, on your graph there, the solutions of the compound inequality are between 2 numbers. All right, like I have here, between 1 and 3, I can make this connected inequality like that. All right, so I have the solutions, great. The numbers between 1 and 3, including 1, right? 1 satisfies both, but not including 3, right? 3 doesn't satisfy this first inequality here. I've got the graph. I can write it as a connected inequality if I wish, because our solutions are between 2 numbers. And then finally, we're asked to, put the solution set in interval notation. Now, if you recall, right, again from previous videos, you're always writing intervals for your solutions from left to right. So going from left to right here, looking at just the solution set, we're going from 1 to 3. So I write 1, 3, right? And that's it. Not to infinity or negative infinity, but the solution set just goes from 1 to 3. So I write 1, 3, and 1 is a solution, right? 1 does satisfy both inequalities. So in order to indicate that, I put the rectangular bracket around 1, just like in my graph. And 3 is not a solution because 3 doesn't satisfy both. It satisfies the right one but not the left one. So to indicate that 3 is not a solution to this and inequality, I put it, cap it with a parenthesis. All right, just like I did in the graph. All right, and there you go. Here's the interval notation, describing this set of solutions to this and compound inequality. All right, so a lot of stuff here. All right, in this first example. Now I'm only going to explain this in this much detail in this first example. All right, the rest of these I'll go a little more quickly. So first, you solve both inequalities. I would, again, I'll graph one on top, one on bottom of the same number line. And if it's an and inequality, you're looking for the intersection. You're looking for the numbers that are on both graphs, numbers that satisfy both inequalities at the same time. I'll talk about OR inequalities in a separate video. And if for some reason the solutions in that overlap are between 2 numbers like we have here, 1 and 3, you can write a connected inequality. You can change that and inequality into a connected inequality like this if you wish, where your solutions are between two numbers. And if one of the ends is a solution, you put the or equal sign. If one of the ends is not a solution, you don't. Right? And then interval notation going left to right. Okay, great. All right, so let's keep doing this. Next example, same instructions. Okay, got the same instructions. Solve the compound inequality, graph the solution, and again I'm going to make like two graphs, one where I graph both of them, and then the final graph where I just show a picture of only the numbers that are solutions of the compound inequality, and then interval notation. Right. So now I got a couple examples per page here. Alright, so again, starting off with some pretty simple examples where both inequalities are already solved. Right, the variable is already alone on one side, and then they're connected by the word and again. Right, all these are connected by the word and. So x is less than or equal to 4, and x is greater than negative 2. Alright, so it's already solved. Wonderful. Then again, off to the side, I'll make my rough graph. And I'm not going to write the words rough graph and final graph after this example. First one I'll put on top, x is less than or equal to 4. So I'll mark off where 4 is somewhere. And that's all the numbers to the left of 4, and including 4. Right? So bracket or close point. And then the next one is x is greater than negative 2. Now negative 2 is to the left of 4 on the number line. Here's negative 2. And x is greater than negative 2, so all the numbers to the right of negative 2, but not including negative 2. Right? So a parenthesis or an open point on that. Now I'm looking for the overlap. Right? The word and is there. I need to find all the numbers that make both true. Well, those are all the numbers. Hopefully you can see that all the numbers between negative 2 and 4 are included, are solutions to both, so solutions to this compound inequality. The number 4 is on both, but the number negative 2 is not. All right, negative 2 is in the top graph, but not on the bottom graph, right, because there's parentheses there. All right, so my final graph here's number line. Again, the numbers negative 2 and 4 are there. And all the solutions are the numbers between negative 2 and 4, right? They satisfy both. Negative 2 does not satisfy both, so parentheses or an open point on negative 2. 4 does satisfy both, so a rectangular bracket or a close point. All right. So there, I'm going to bubble this in. This is what I would hand in if I were doing this as a homework assignment for a professor. And then the interval notation for this, left to right, going from, the solution set here is going from negative 2 to 4. Negative 2 is not a solution to both. Right? Negative 2 is not a solution to the compound inequality. 4 is. So a bracket on 4, and there you go. There's your interval notation for this particular compound inequality. Additionally, if you would like, again, notice that my solutions are between, the bulk of the solutions are between two numbers. So I could, if I wanted, say, hey, the solutions to this are values of x, right? Again, the variable was x, that are between negative 2 and positive 4, right? Like this. And again, make sure the number on the left is smaller to the left of the number on the right on the number line. So all the values between negative 2 and 4, right, greater than negative 2 and at the same time less than 4. Negative 2 is not a solution, but 4 is, so I'm going to put the or equals to by the 4 there. Right? So you could also write the inequality this way as a connected inequality because the solutions are between two numbers. Right? This is the only time you can do this, is when your solutions are between two numbers like this. Okay. All right. Next example. So again, this time I'm not going to write, again, both inequalities are already solved. They're connected by the word and. So same kind of thing as the first two examples. So I have the solutions to this are going to be the numbers that make both of these true, right? Numbers that are both greater than or equal to -4 and at the same time less than or equal to -1. All right, so let me draw these in my rough graph here. Here's -4. All the numbers, greater than or equal to -4 are the numbers to the right of -4 and including -4. So a bracket on that. And all the numbers less than or equal to -1. All right, so here's -1 should be to the right of -4, and I'll draw this graph below. Now less than -1 is to the left, including -1, right? Bracket on that. And then the inequalities are connected by the word and. So not all these numbers are considered solutions, just the ones that satisfy both, just the ones in the overlap, which would be all these numbers in between -4 and -1, and including -4 and -1, right? -4 is on both graphs. -1 is on both graphs. So the final graph, right, the one I would hand in, here's -4, here's -1, and we're talking all the numbers in between -4 and -1 satisfy both inequalities. -4 satisfies both. -1 also satisfies both. So I put brackets or closed points on both ends. So there's the final graph, right? Interval notation. Again, look at the picture. Go from left to right. It's going from -4 to -1. This piece of solutions. -4 is considered a solution of the compound inequality, and so is -1. So there is your interval. And if you have the bracket on both ends like this, this would be called a closed interval. I'm not going to write that. You don't really need to know that right now. And additionally, if you want, because the solutions are between two numbers, we can make a connected inequality. I can say the values of x that satisfy this compound inequality are between, right, a little less than, between -4 and -1, and including both of them. So I have less than or equal to, right? So you could also write this connected inequality, and these mean the same thing, right? These mean the same thing, both these inequalities. But and one more time here, the only time you can do this is if your solutions are, between two numbers. Okay. Example 4. Same instructions. Now, yet again, this is the last example where the inequalities are already solved, right? The variable is already alone. So I'm looking for all the numbers that are both greater than -6 and less than -3. So again, off to the side, I'll make a rough graph. Now -6 is somewhere, -3 would be to the right of -6. And again, just make sure you're putting your numbers in the proper places on the number line. Greater than -6 are the numbers to the right of -6, but not including -6, so I got a parenthesis on that. X less than -3, those are all the numbers less than 3 left of -3, but not equal to -3, right? So parenthesis on that. And we're looking for the overlap, right? And we're looking for the intersection, the numbers that satisfy both. And again, we'd have just these numbers here, just the numbers between -6 and -3. But not -6, right? -6 on the second graph, but not the first one. Not -3 either, right? -3 is on the first graph, but not on the second graph. All right, so my final graph, right, the one I would hand in, here's, -6, negative 3, and our solutions to this compound inequality, the numbers that satisfy both are the numbers between negative 6 and negative 3, but not including negative 6 nor negative 3. All right, and again, I'll put this in a circle. This is what I would hand in. Then the interval notation, we're going from negative 6, from left to right, from negative 6 to negative 3 with this picture of solutions, but not including either one. Right? So parentheses on either one of those, and there's the interval notation for the set of solutions. And if you have parentheses on both ends, this is called an open interval. Right? In my examples earlier, where there was a parenthesis on one end, bracket on the other, this is called half open or half closed or clopen. But again, you really don't need to know all that yet. And once again, because my solutions are between two numbers, I can take this inequality and write it as a connected inequality. My solutions, the values of x that satisfy this compound inequality, are between, right, so little is less thans on either side, between negative 6 and negative 3. So negative 6 on the left side here, negative 3 on the right side. And you can write this connected inequality, and it has exactly the same meaning. Right? It describes exactly the same numbers. Okay, and no or equal to on either of these, because negative 6 and negative 3 are not solutions. Alright, so now from here on out, alright, the following examples 5 through 26, you actually have to do some solving first. Alright, they're still connected by the word and, so it's still considered a compound inequality. And we're looking for the numbers that satisfy both of these, right? What values of x can I use to make both of these true statements? Not just one or the other, but both. Alright, so as I mentioned at the top of the video, I'm assuming you know how to solve inequalities in multiple steps. Alright, so I'm just going to kind of breeze through the solving part. I'll write a few things, but I'm not going to write every single little thing I'm thinking. Alright, I'll just say it out loud. So like this one here, I would add 2 and then divide by 5. We'd have 10 divided by 5, and then the inequality wouldn't change, alright, because I didn't multiply or divide by a negative number ever. So when I solve this, it would be x is less than 2. Alright. And solving this inequality, right, first I would subtract 9, giving me 3 minus 9, negative 6 over here, and then divide by 6, giving me negative 1. Right, x, and the inequality wouldn't have flipped because I never multiplied or divided by a negative number, and I never switched sides with the expressions. Okay, so here I've solved the compound inequality. Right, we have a description of the solutions here. I may be able to write this in a different way, right? Maybe as a connected inequality or something like that. Make a rough graph off to the side. Now the numbers that are mentioned here are 2, positive 2, and negative 1. And negative 1 would be to the left of 2 on the number line. X is less than 2. That's these numbers. Right, all the numbers left of 2, but not including 2. X is greater than or equal to negative 1. That's all these numbers to the right of negative 1 and including negative 1. And we're looking for overlap. What numbers are on both? Well, negative 1's on both, right? All the numbers from negative 1 to 2 are on both, but 2 is not on both. 2's on the second graph, but not on the first graph, and that's it. Those are the only numbers that satisfy this compound inequality. Alright, so the final graph will be, here's again negative 1, here's positive 2. And the final graph will consist of all the numbers between negative 1 and 2, including negative 1, so bracket there, not including 2, parentheses there. All right, and also, again, I'll circle this because that's going to be what I'd hand in, the final graph. And then interval, going left to right for this picture. This is going from -1 to 2, including -1, right? So bracket there, not including 2, parenthesis there. There's the interval notation. And yet again, since my solutions are between two numbers, we can write this inequality as one of those connected inequalities. I could say the solutions, the values of x that make this compound inequality true, are the values of x that are between -1 and 2. So again, little less than is less than on both sides, -1 on the left, +2 on the right. Again, make sure these are in the proper order. Lower number on the left, larger number on the right. -1 is a solution, so I put the or equals to next to the -1. 2 is not a solution, so I don't do it for 2. Right? You could also express the inequality this way. Both these inequalities mean the exact same thing. Right? They're describing the exact same numbers. Just wanted to point that out again, that if solutions are between two numbers, you can do this. You can make this connection. Okay. Next example. All right, so example 6, and same setup. Another pair of inequalities connected by the word and, making a compound inequality. So first step is solving both. Now, like I said, I'm not going to write out every little step. I'll tell you what I'm thinking, and then write the solutions at the end. So for this one, I would add 1, giving me 8 on the right side, and then divide by 4, and 8 divided by 4 is 2, so we'd have x is less than 2. And notice the is less than wouldn't have changed because I never multiplied or divided by a negative number. And for this one, I would subtract 8. 4 minus 8 is -4. Then -4 divided by 2 is -2. And again, the inequality wouldn't have changed because I never multiplied or divided both sides by a negative number. Right. So here we go. Now let's make the rough graph. I got 2 and -2 are mentioned. There's, say, +2 there. -2 would be to the left of +2. X is less than 2. That's all the numbers left of 2, but not including 2 up top there. X is greater than or equal to -2. That's to the right of -2 and including -2. And again, we've got an and inequality, so I'm looking for the numbers that satisfy both. Now, -2 is on both. All these numbers between -2 and +2 are on both. But then +2 is not on both. Right? So +2 is not a solution of the compound inequality. All right, so the final graph, here's the number line, there's -2, +2. It's all the numbers between -2 and +2. -2 is a solution of the compound inequality, +2 is not. Right? So bracket on -2, or a closed point on -2, and a parenthesis or an open point on +2. There's your final graph. As for the interval, going left to right, this is going from -2 to +2, so -2, 2 here. Bracket on -2 because it is a solution. It does satisfy both inequalities at the same time. And a parenthesis on +2 because it doesn't satisfy both. And once again, just like in the previous examples, all my solutions are between two numbers. So I can write one of those connected inequalities if I wish. All the values of x that make this compound inequality true are the values of x that are between, right, so x between -2 and +2. Including -2 but not including +2. So I put the or equals to next to the -2 there. Right, so you could write the solutions this way as well, or write the inequality this way, and it has exactly the same meaning. Okay. Example 7. Very, very similar. Right? Same setup. We'll solve both and then look for the numbers that satisfy both at the same time, right, with the word and in the middle there. Alright, so this side subtract 6, that would give me -4, and then divide by 4 give me -1, and the inequality would not flip. Alright, so I have x is less than or equal to -1, and here subtract 1, giving me -6 on the right, divided by 2 would give me -3 on the right, and the inequality wouldn't flip. X is greater than or equal to -3. Alright, so rough graph, -1 and -3 are mentioned. Here's say -3, -1 would be to the right of -3. Alright, be careful with negatives. Less than or equal to -1 would be this picture. Greater than or equal to -3 would be this picture. And you can hopefully see the overlap, right? The numbers that satisfy both. -3 is on both graphs. -1 is on both graphs. And everything in between is also on both graphs. So everything from -3 to -1 belongs on the graph of the solutions of this compound inequality. So everything between -3 and -1, including both -3 and -1, right? So brackets on those. So there's your final graph. Writing the solutions in interval notation, right? This piece of solutions is going from -3 to -1, so -3 comma -1, including both, right? Both -3 and -1 are solutions, so I put the little rectangular brackets on both of those. And once more, all our solutions are between two numbers. So I could, if I wanted, take this inequality and write it as one of those connected inequalities, right? The values of x that satisfy this compound inequality are between -3 and -1. -3 on the left, -1 on the right, including them, right? So I got the or equals to on both of those. Right? And this inequality is exactly the same as this inequality with the word and. They mean exactly the same thing. And you can go back and forth between them if you wish. Alright, next example. Same stuff, just kind of over and over again. Maybe eventually we'll get to an example where the solutions aren't just in between two numbers. Then you can't make one of those connected inequalities. Alright, so example 8. This first inequality, 4x minus 2 is less than or equal to 4. I'd have x, I would first add 2 to get 6, and then divide by 4 to get 6/4, which reduces to 3/2, or 1.5. 6/4, 3/2. And again, the inequality wouldn't have changed because I never would have divided by a negative number, right? So I have x is less than or equal to 3/2. And over here, I would add 1 to get -7. Right, -8 plus 1 is -7. Then divide by +7, to get -1. And the inequality would not have flipped. So x is greater than -1. Make a rough graph. Now +3/2 would be, to the right of -1. X is less than or equal to 3/2. That's this picture here on top. X is greater than -1. That's this picture here. Right. And the overlap, right? -1 is not on both graphs, but all the numbers in between -1 and 3/2 are, and then 3/2 is also on both graphs. Right. So the final graph here, -1 to 3/2. The solutions to this compound inequality are all the numbers between -1 and 3/2, not including -1, right? -1 is not on both. 3/2 is. Right? So parenthesis on the -1 bracket on the 3 halves. So there's your final graph. Interval notation for this picture. It's going from left to right here, from -1 to +3 halves, not including -1, but including 3 halves, right? So parentheses on the -1, bracket on the 3 halves. There's your interval notation for this set of solutions. And yet again, the solution picture here, all the solutions are between two numbers, so I can, if I want, write this connected inequality, say all the values of x that satisfy this compound inequality are between -1 and +3 halves, not including -1, but including 3 halves, right? So the or equals sign under that inequality symbol there, and you can you could express this inequality in this way if you wished as well. It means the same thing. Okay, so kind of on a roll here. All right, next one, example 9. This inequality, I'd add 11 to get 16, divide by 2 to get 8, and the inequality would not have flipped. So x is less than 8. And here I would add 8 to get +3, divide by 3 to get +1, and the inequality would not have flipped. Right, so x is less than 8 and x is greater than 1. I make a rough graph off to the side. Now 8 and 1 are mentioned. 1 would be to the left of 8 on the number line. X is less than 8 would be this picture on top. X is greater than 1 would be this picture on bottom. And again, the overlap is all the numbers between 1 and 8. Right? All the numbers that satisfy this compound inequality are the numbers that are on both graphs at the same time, that satisfy both. Now 1 is not on both. 1's on the top graph but not on the bottom graph. 8 is not on both, right? It's on the second graph but not the first one. So just the numbers between 1 and 8 are on my final graph. So here's 1, here's 8. And it's just the numbers in between, right? Not including 1 or 8. Right? So parentheses on both of those. So there's the final graph. Again, pretty easy interval notation, going left to right here. You're going from 1 to 8, so 1 comma 8. Parentheses on both, because neither 1 nor 8 are considered solutions of the compound inequality. Right? Neither one of them satisfy both inequalities. And once again, since my solutions are between two numbers, I can express this inequality with the word and as one of these connected inequalities. Say the values of x that satisfy this compound inequality are between, right, like this, 1 and 8. 1 on the left, 8 on the right, not including either one. Right? So you could express this inequality this way, and they mean the exact same thing. Right? Describe the exact same numbers between 1 and 8. Okay, example 10. So again, I'm going to solve both inequalities. They're also connected by the word and, making it a compound inequality. All right, so for this side, add 8 to give me 14 on the right, and then divide by 7. 14 divided by 7 is 2. So x is less than 2, right, and the inequality wouldn't have flipped. I didn't multiply or divide by a negative. And for this one, I would subtract 7 to give me -10 on the right, then divide by +5 to give me -2 on the right. X is greater than -2. Doing a rough graph on the left, on the right side here, you have -2 is mentioned, +2 is mentioned, right? -2 would be to the left of +2. X is less than 2 is this picture on top. X is greater than -2 would be this picture on the bottom. And the overlap, right, the solutions to this compound inequality are all the numbers between -2 and +2, right? All those numbers are on both graphs. -2 is not, all right? +2 is not. Just the numbers between negative 2 and positive 2. So here's negative 2, positive 2, and our graph is just the numbers between those, but not including them, right? So parentheses on both of those. So there's our final graph. The interval notation, right, going from left to right are, it's the numbers from negative 2 to positive 2. So I put negative 2 comma 2. And neither one of those ends, negative 2 nor positive 2, are solutions of the compound inequalities. So I put parentheses on both ends. And once again, if you want to rewrite this inequality, you can, because the solutions are between two numbers, and only when the set of solutions is between two numbers can you make this connected inequality. The values of x that satisfy the compound inequality are values between negative 2 and positive 2. Right, and then don't put the or equals on either of those, because negative 2 nor positive 2 are included. Okay. So again, I'm not going to write out every little step. I'm just going to describe how I would find the solutions to these. So this one I would divide by the 4, right, to make this 3. Then add 1. 3 plus 1 is 4. Divided by 2 is 2. So x is less than or equal to 2 would be the set of solutions to that first inequality. All right. And again, I never multiplied or divided by a negative number, so the inequality symbol wouldn't have changed, wouldn't have flipped. Here, I would divide by 2 to make that 2, and subtract 1 to make it 1. X is less than 1. All right. Again, I never multiplied or divided by a negative, so the inequality symbol wouldn't have flipped. Okay. Rough graph off to the side. Now the numbers mentioned in each of these are 1 and 2, so and 1 would be to the left of 2. X is less than or equal to 2. So above, on the top of the picture, I'll draw that. That's that picture there. X is less than 1. That's this picture here. Look at this. This is finally a different kind of example. So now the solutions aren't going to be between 1 and 2. All right. Look, the numbers between 1 and 2 are on the first graph, but not the second one. So they do not solve the compound inequality with this and word here. The numbers that are in the overlap are all the numbers to the left of 1, right? Forever. But not 1 itself, right? 1 is on the first graph, but not on the second graph. So the only numbers that are going to be on my final graph are the numbers left of 1. So that's all I need to draw. The final graph are just the numbers less than 1, but not including 1. That's it. Simple as that. Right, those are the only numbers that satisfy both, that are on both graphs. So there's not even any need to put the number 2 on here. Right. And interval notation, remember this piece of solutions here going left to right, there is no left end, so I indicate that with negative infinity, and it goes until you hit 1. Always parentheses, right, on infinities, because those are not numbers. And as I mentioned, 1 is not a solution. 1 does not satisfy both inequalities, so a parenthesis on that. And really, this compound inequality can be boiled down to just simply x is less than 1. Those are the only numbers that satisfy both. That would be a simpler version of the compound inequality. So yeah, so the only numbers that satisfy both are the numbers less than 1. And you can very easily see that from the graph, this rough graph over here. Looking for overlap, looking for intersection. Okay, great. All right, and hopefully we see more examples like this. All right, number 12. Again, I'll just kind of describe out loud the solution. So I would divide by 5 first, making this a 1. Then add 2. 1 plus 2 is 3. Then divide by 3. I'd get 1 on the left side, on the right side, and I never multiplied or divided by a negative when I spoke, so the inequality wouldn't flip, the inequality symbol. So the solutions of this first inequality are, the numbers less than or equal to 1. But don't forget we're, and the solutions of this one. So here I would divide by 3, making that a 1, and then subtract 3. 1 minus 3 is negative 2, and we wouldn't change the symbol. So x is less than or equal to 1, and at the same time, x needs to be less than negative 2 as well. So again, off to the side, I'm going to make a rough graph. Now the numbers mentioned are positive 1 and negative 2, right? And make sure you're marking them in the correct places. Negative 2 would be to the left of positive 1. X is less than or equal to 1. That would be this picture on top. Right. X is less than negative 2. That would be this picture on bottom, not including negative 2. And I'm looking for overlap, right? Again, I'm looking, this is pretty much like the previous example. I'm looking for all the numbers that are on both graphs, right? It's an and inequality. Well, that's just these numbers. Right? The numbers to the left of negative 2 are on both. Negative 2 is not on both. It's on the first one, but not the second one. And all these numbers, from negative 2 to 1, they're on the first graph, but not on the second graph. So they don't belong to the final picture. Right? So the solutions of this compound inequality are only the numbers left of negative 2. So on my final graph, I only need to mention negative 2. I only need to mark off negative 2. And the numbers that satisfy the compound inequality are the numbers less than negative 2, but not negative 2 itself, right? So I'm putting parentheses on that. Negative 2 itself is not on both graphs. Doesn't satisfy both, right? So only the numbers less than negative 2. And then interval notation, going left to right here, that'd be from, negative infinity up to negative 2, right? But not including negative 2. So I got parentheses around that. And if you take a look at this graph, this compound inequality basically just boils down to the numbers less than negative 2. There's a simpler description of the solutions. All right, so yeah, this entire compound inequality is equivalent to just saying x is less than negative 2, right? Those are the only numbers that satisfy both. Okay. So yeah, very similar setup, very similar examples, number 11 and 12. See what happens in number 13. All right, so for number 13, again, I would, to solve this, get the variable alone on the left, I would divide by 3. I would turn this into 1 on the right. I would then add 3. 1 plus 3 is 4 on the right. And then divide by 2. 4 divided by 2 is 2. So I'd end up with 2 on the right. And then the greater than wouldn't change. It wouldn't flip. I never multiplied or divided by a negative. So that ends up x is greater than 2. And here, first I would divide by 4, making this 1. Then I would subtract 5. 1 minus 5 is negative 4. So I'd have x is greater than or equal to negative 4. And again, the symbol wouldn't have flipped because I never multiplied or divided by a negative number. And again, I leave all the steps for you to write. All right. Okay, then a rough graph off to the side. Now the numbers mentioned here are positive 2 and negative 4. X is greater than 2 would look like this. I'll put that on top. X is greater than or equal to negative 4 would look like this. And I'll put this on the bottom. And again, we're looking for, because the word and is the connector here, we're looking for the numbers that satisfy both. Well, these numbers from negative 4 to 2 are on the second graph, but not the first one. So they won't belong on my final graph. Positive 2, it's on the second graph, but not on the first one. So that doesn't belong either. the only numbers that are going to belong to my graph, the only numbers that are solutions to this compound inequality are the numbers greater than 2. So on my final graph, I'm simply just putting the numbers greater than 2, all right, but not 2 itself. All right, in parentheses on 2. So there's the graph I would hand in to if this were an assignment. And then interval notation, right? This picture here goes from from left to right. You're going from 2 to infinity, not including 2 though. So parentheses on the 2 and always parentheses on the infinities. And then from this graph, I can make a simpler inequality. Right? Instead of writing out this whole compound inequality with the word and, it looks like it boils down to just the values of x that are greater than 2, right, but not equal. All right, so this inequality here is equivalent to this compound inequality. Right? They describe the same set of numbers. Okay, let's keep going. All right, example 14. So again, I'm just going to describe the solutions. Now, first for this one, I would divide by -3. Now dividing by a negative will change the symbol. So that is less than will become is greater than. I'd still have 0 on the right. 0 divided by any non-zero number is still 0. And then I'd subtract 4. 0 minus 4 is -4, and then the x would be alone. So the solutions to this inequality are the numbers greater than -4. And same deal here. The first thing I'm doing is dividing by a negative number. Right, to get rid of this factor of -1, I would divide by -1, changing this is less than or equal to is greater than or equal to. You'd then have -7 on the right. I would add 1 to make it -6, and then divide by 3 to make it -2. And then x would be alone on the left. But yeah, so I divided by negatives here, so that would flip the symbols, right? It becomes is greater than, this becomes is greater than or equal to. So here's a description of some solutions. Again, let's see if we can boil it down, make it simpler. I'm going to make a rough graph off to the side. Now the numbers mentioned are -4 and -2. And -4 should be to the left of -2. X is greater than -4. That'd be this picture. I'll put that on top. X is greater than or equal to -2. That's this picture. And I'll put that on the bottom with a bracket. And we're looking for overlap, right? Again, the connecting word here is and. So I'm looking for numbers that satisfy both inequalities at the same time. That would be all the numbers to the right of -2 and including -2 this time, right? The numbers to the left of -2 though are, these numbers up to -4 are on the first picture but not the second one. So we're only on the final graph. I'm only going to put -2 and all the numbers to the right of -2. So again, the only number that needs mentioning here is -2. And it's all the numbers to the right of -2 satisfy both, and -2 itself, right? So I put a bracket on it. It satisfies both. It's on both pictures. So there's your final graph, right? The one I would hand in. And then interval notation, right, from left to right. This goes from -2 to positive infinity. -2 is a solution, satisfies both inequalities. So bracket on that, and always parentheses on infinities. And then the simplest way to write the solutions, looking at this picture, would just be, x can be any number greater than -2 or equal to -2. There's the simplest way to describe the solutions of this compound inequality. And they have the same meaning, describe the same set of numbers. Okay. Wonderful. All right. Next. And I'll solve them out loud. If you want, I leave the writing of the steps to you. So this first one, to get rid of the fraction, I would multiply by 2. All right, multiply by 2. That would give 2 on the right side. Then I would add 4 to make 6 on the right side. and then divide by 3 to give 2 on the right side. So x is less than or equal to 2. And again, at no point did I multiply or divide by a negative number. So the inequality stays the same direction. So I have x is less than or equal to 2, and this one here, to get rid of the fraction factor, I'd multiply by 3 to make 12, then subtract 6 to make 6 on the right side. So x is less than or equal to 6. Okay. And again, at no point did I multiply or divide by a negative, so it still is less than or equal to. Off to the right here, I'm going to make a rough sketch, a rough graph. The numbers mentioned in both of these are 2 and 6, right? And 2 would be to the left of 6. X is less than or equal to 2 would look like this, right? All these numbers here on top. X is less than or equal to 6 would look like this, all these numbers on the bottom here. And we're looking for overlap. Again, the connecting word is and, right? We're looking for the numbers that satisfy both inequalities. That would be all the numbers to the left of 2, right? They're on both graphs. Also 2 itself. And that's it. All right, the numbers to the right of 2 are not on both graphs, so they don't satisfy both inequalities. So on my final graph, the only number that needs to be mentioned is 2. So there's 2, and the only numbers that satisfy both inequalities are the numbers to the left of 2 and 2 itself. Right, so I bracket on 2. So there's the final graph. The interval notation for this, right, going left to right, this is going from negative infinity, right, far left forever, up until positive 2. Always parentheses on the infinities, and 2 is a solution, right, so I got a bracket on the 2. And then from the graph, we can make a simpler version of the inequality. Right? This compound inequality is equivalent to just saying x is less than or equal to 2. And it's a much simpler way of writing the solutions instead of x is less than or equal to 2 and x is less than or equal to 6. Right? The only ones that satisfy both are the ones less than or equal to 2. So that's all I need to write for the solutions. Okay, moving right along. Exercise or example 16. Again, same deal. I'm just going to solve it out loud. I'll leave the steps to you to write out. Again, I'm assuming you know how to solve multi-step inequalities. Alright, so for this, to get rid of the fraction factor, I would multiply by 4/3. Now if I multiply this side by 4/3, that would just be 4. And then I would add 8 to make 12. So x is less than or equal to 12. And again, at no point did I multiply or divide by a negative number, so the inequality would never have flipped. And this one, to get rid of the 1/5 factor, I would multiply by 5. That would make this side 15. And then I would add 5 to get x alone. 15 plus 5 is 20. So, and again, the inequality would not have flipped at any time. Right? So x is less than or equal to 20. Off to the side, I'm going to make a rough sketch of both graphs. The numbers mentioned are 12 and 20. X is less than or equal to 12. I'll put that picture on top. Right, that's that picture there with the bracket on 12. X is less than or equal to 20. That's this picture on, I'll put that on the bottom. Right. And again, the connecting word is and. So we're looking for numbers that are on both graphs. We're looking for the overlap, the intersection. So that's all these numbers, right? All the numbers to the left of 12, including 12, are on both graphs. The numbers to the right of 12, from 12 to 20, they're on the second graph, but not the first one. So those are not included. The only numbers that are included in my solutions to this compound inequality are the numbers less than 12 or 12 itself. Right, so on my final graph, the only number that needs mentioning is 12. And all the numbers to the left of 12 are solutions, and 12 itself. So a bracket on 12 or a closed point on 12. So there's the final graph. Then the interval notation, right, looking at my picture, going left to right here, we have from negative infinity up to 12, right, so negative infinity, comma 12, always parentheses on the infinities, and 12 is a solution. 12 does satisfy both inequalities, so a bracket on 12. Right. There's your interval notation. And then, as in previous examples, we can take our graph and make a simpler version of the compound inequality. Right, all the solutions here are values less than or equal to 12. Right, so this whole compound inequality is equivalent to just saying x is less than or equal to 12. I'd rather write the solutions that way instead of writing all that. Great. All right. Next example. Again, the word "and" is our connector. It's a connector for all of these. Again, I'll just say all the steps I'm performing out loud, and I'll leave you to write the steps for yourself. Of course, most instructors would ask you to write all the steps out. I'm not handing this in to anyone, so I'm just going to say them out loud. So here I'd subtract 3x, right, giving me 2x. Maybe I'll just at least write that one step, right? 2x here, I'd add 2 to get 6 over here, and then divide both sides by 2. X is less than or equal to 3 for that first inequality. And here I'd subtract 2x, giving me 1x over here is greater than or equal to 5, right? I would add 4. So x is less than or equal to 3, and x is greater than or equal to 5. All right. And rough sketch over here, I'm going to make a rough graph. The numbers mentioned are 3 and 5, right? 3 would be to the left of 5. X is less than or equal to 3. I'll put that up top. That's this picture. Right. X is greater than or equal to 5. I'll put that on the bottom. That's this picture. And we're looking for numbers that are on both graphs at the same time, right? The overlap, the intersection. Well, there is none, right? There's no overlap. There are no numbers that are on both graphs. There are no numbers that satisfy both of these inequalities at the same time. So that means this compound inequality has no solution. Right? There is no number that you could replace x with and make both of these true at the same time. So they might say that the solution set is the empty set. You might see this in some texts where it's just an empty set of curly braces, or a circle with a slash through it. All these symbols mean is that there's no solution. There's no number in the solution set. No number that makes this compound inequality true. Okay? Great. All right. Next example, example 18. Again, I'll just describe how I solve these. Maybe write one of the steps out. So here I would add 5 first. Right? You'd have 3/4 x is greater than or equal to 3. Right. And then I would multiply both sides by 4/3, which would give me 4 on the right side. And notice I never multiplied or divided by a negative. Right? So the inequality symbol would not change. And here I would divide by -3 first. That would flip the symbol, so is greater than or equal to becomes is less than or equal to, and then 6 divided by -3 is -2. And then I would subtract 1 to give me -3 on the right side. So I have x is greater than or equal to 4, and x is less than or equal to -3. And off to the side, I'm going to make a rough graph where I put both of them on the same number line. The numbers mentioned are -3 and +4. X is greater than or equal to 4. I'll put that on top. That's these numbers. x is less than or equal to negative 3. I'll put that on bottom. That's these numbers. And yet again, as in example 17, there's no overlap. All right, this is an and inequality, so I'm looking for overlap. I'm looking for numbers that are on both graphs, numbers that satisfy both inequalities. Well, that's not happening. So yet again, just as in example 17, this compound inequality has no solution. There is no number that you could replace x with and make both of these true at the same time, make this compound inequality true. All right. And as in example 17, you could also say the solution set is the empty set. Okay, 19. All right, so I would add 6. That would make positive 2 over here. Then to get rid of the fraction, I multiply by 3 halves. 2 times 3 halves would be 3. So I'd have x is greater than or equal to 3. Right, and at no point did I multiply or divide by a negative number, so that's why the inequality symbol didn't flip. And here I would divide by a negative. You'd have x plus 2 is less than or equal to 0, right? Dividing by negative 4. That flips the symbol. And then subtracting 2 gives me negative 2 on the right side, so I have x is less than or equal to negative 2. So x is greater than or equal to 3, and at the same time I need x to be less than or equal to negative 2. Go off to the right here, I make a rough sketch. The numbers mentioned are positive 3 and negative 2. X is greater than or equal to 3 are these numbers. Put that on top. X is less than or equal to negative 2. Those are these numbers on the bottom here. And I'm looking for numbers in the overlap. Well, again, there's no overlap. There are no numbers that satisfy both inequalities. So as in examples 18 and 17, there is no solution to this compound inequality. No number you could replace x with to make both of these statements true, right? To make the compound inequality true. All right. Let's look at another example. I got 26 of these. And again, you can skip around by clicking on the timestamps in the description of the video. Okay. So here, first I would subtract 2, giving me negative 7. Then to get rid of the half, I'd multiply by 2. All right, negative 7 times 2 would be negative 14. And then I would add 6 to get x alone. Negative 14 plus 6 is negative 8. So x is less than negative 8. And again, at no point did I multiply or divide by a negative number. So the inequality would not change. The inequality symbol would not flip. And now here, I'd subtract 4, giving me negative 2/3 x is less than 2. And I would multiply by negative 3 halves. So that would flip the symbol from is less than to is greater than, right, because I'm multiplying by a negative. And 2 times 3 halves would just be 3, so it would be negative 3. Right? Negative 2 times negative 3 halves would be negative 3. So I have x is less than negative 8, and x is greater than negative 3. So the numbers mentioned are negative 8, negative 3, and don't forget, negative 8 would be to the left of negative 3. X is less than negative 8. That's these numbers. X is greater than negative 3. That's these numbers. And yet again, as in the previous several examples now, there's no overlap. Right, there's no intersection. There are no numbers that satisfy both of these inequalities at the same time, which needs to happen when you have the AND connector. So just as in the previous several examples, this compound inequality again has no solution, or the solution is the empty set. Okay, now for the final 6 examples, 21 through 26. If you remember early on in the video, right, examples 1 through 10 maybe, I mentioned connected inequalities, right? This is an example of one of those connected inequalities where you have the two, put together without, and you don't see the word and, but it's implied to be there. All right, this connected inequality saying -5 is less than or equal to 4x minus 1, which is less than 7. This is equivalent to saying the following, saying that -5 is less than or equal to 4x minus 1 and 4x minus 1 is less than 7. So both of these, share that middle part, right? The 4x minus 1 is in both inequalities. So one more time, -5 is less than or equal to 4x minus 1, one inequality, and 4x minus 1 is less than 7, right? You got a left inequality and the right inequality. So these are equivalent. Right? Whenever you see a connected inequality like this, it's equivalent to one of these and compound inequalities. All right, so just as before, I'll solve both. All right, now I would add 1, giving me -4 is less than or equal to 4x, divide by 4, giving me -1 is less than or equal to x, which, if you read it the other way around, would be x is greater than or equal to -1, right? Remember, switching sides changes the inequality symbol, flips it. And here I would add 1, give me 4x is less than 8, and divide by 4, giving me x is less than 2. So I get x is greater than or equal to -1, and x is less than 2. And I'll tell you right now, the graph of this will look like this. You have -1 is mentioned, 2 is mentioned. And if you recall from before, again, early on in the video, when you have these connected inequalities, it implies that there is some sort of betweenness. So when you find your solutions to these connected inequalities, these and inequalities, the solutions will be between two numbers. And these numbers here are -1 and +2, so you'll have these. All right? Numbers greater than -1 and at the same time less than 2. That means you're between -1 and 2. Now notice we have greater than or equal to -1, so -1 is a solution, right? It does satisfy both, right? -1 is equal to -1, -1 is less than 2, it satisfies both. The other end though, 2, sure, 2 is greater than or equal to -1, but 2 is not less than 2. Notice we had x is just less than 2, so 2 is not included. And there's your graph. All right. So there's the graph of the solutions. The interval from -1 to +2, including -1, not including 2, right? So bracket on -1, parentheses on +2. Now you may have noticed that when I did this, when I split this up to write the word and, in both of these inequalities, the left inequality and the right inequality, I used the same steps to solve, right? I added 1 to both sides, then I divided both sides by +4. So rather than do that, rather than split them up, just use steps to get the variable alone in the middle. You can solve these connected inequalities the way they look at the beginning. Use steps to get the variable in the middle. All right, and what you do to one part, you do to all three. All right, so here are the final solutions here, okay? The graph and the interval. But let me do that off to the side. So we had negative 5, right, is less than or equal to 4x minus 1, and 4x minus 1 is less than 7, right? So an and inequality. And then I would perform the following steps, right? The same steps I did in both of these. To get the variable alone in the middle, I want x alone in the middle. So first I would add 1, and if I add 1 in the middle here, I'm going to add 1 to both sides of both inequalities, right? So add 1 to all three parts. And that would give me negative 4 is less than or equal to 4 times x, and 4 times x is less than 8. Right? And you see that that's here. Negative 4 is less than or equal to 4 times x, and 4x is less than 8, right, after adding 1 to everything. But I'm just kind of doing it all at the same time over here, keeping things connected. Right, and then, to get the x alone in the middle, I would divide by 4. Now, if I divide by 4 here, I divide by 4 on this side of this inequality, and divide by 4 on this side of this inequality. Just divide by 4 in all three parts. Over here now, you have negative 1 is less than or equal. In the middle, you have just x, and x is less than, and then on the right, you have positive 2. And then you see this connected inequality. Now the variable is alone in the middle, and that's exactly the same any kind of inequality I was writing at the beginning of the video when my solutions were between two numbers, where I was writing these connected inequalities. So when you have these connected inequalities, just keep it the way it is. Remember that it's an and inequality, right? You got two at the same time. And just do all the steps you would normally do, but to get the variable alone in the middle. Right? Whatever you do to the middle part, just do to all three parts. And don't forget the usual rules, right? When you multiply or divide by a negative number, that would change the direction. You would just flip the entire inequality, right? And I don't think I come across any examples like that, but just keep that in mind. If you ever do have to multiply or divide by a negative number in the middle here, and do it to all three parts, that'll just change the direction of the entire inequality. So I would just write it in the opposite direction if I were you. But again, that's not going to really happen here. All right, so my last several examples, as I mentioned, are going to be all these connected inequalities, these and inequalities, where the solutions should be between some numbers. All right. So for this one, I would add 5 to all three parts. All right, and I'll actually write out the steps for the first few of these. So to get x alone in the middle, my first step would be to add 5, right? Get rid of this negative 5 here, and I do it to all three parts. All right, so over here, we have positive 2 is less than, then we have 2 times x left in the middle, is less than or equal to 1 plus 5 is 6. Then, I don't want 2x, I want 1x. Divide by 2. And again, do it to all three parts. And once more, this is a positive number I'm dividing by, so like the inequality stays the direction it is, right? We'd have 1 is less than x, and x is less than or equal to 3. So there's a description of the solutions, right? The variable is alone in the middle. The graph, again, the numbers 1 and 3 are mentioned here. 1 is to the left of 3. And all the solutions are the numbers between, right? All the values of x between 1 and 3. Not including 1, right? Because it's just the less than there. But including 3, because you got the less than or equal to. So there's your graph. And then for the interval notation, as you've seen earlier on in the video, the first several examples, we're going from 1 to 3, right? But not including 3, so parentheses on that. Sorry, not including 1, but including 3, so a bracket on that, and there's your interval notation. Very, very simple. All right. Next example. Again, I'll write the steps out for this one as well. I want to get x alone in the middle of this connected and inequality, right? Just the word and isn't written. It's implied to be there though. So I would take away the 1 first. All right, gives me 4 over here is less than 4x, and 4x is less than 8. and then I divide everything by 4 to get x alone in the middle. And again, this is a positive 4, so the inequality would stay in the direction that it is. You wouldn't flip anything. You know, if I divided by a negative, I would flip the inequality symbols, and personally I would just write it in the other way, and I'll show you an example of that off to the side when I'm done with this one. So we have 1 is less than x, and x is less than 2. There's the description of the solutions. X is any number between 1 and 2, but not including 1 or 2. So here's 1, here's 2. And we're talking about these numbers here, all the numbers between 1 and 2, not including 1, not including 2. So parentheses on those. Then the interval would be from 1 to 2, parentheses on both, right? Neither one's included. And then, as I mentioned, I'll show you a real quick example off to the side. Here's a separate example. You know, so if I had 2 is less than negative 2x, and that's less than 6 or something like that, you know, and I divided everything by negative 2 to get the variable alone, you'd have negative 1 here, and then all the symbols would flip. Right? All the symbols would flip because I'm dividing by negatives on both sides of these inequalities. So this would be is greater than x and is greater than negative 3. And like I said, I would personally rewrite this in the other direction. Right now I have negative 1 is greater than x and x is greater than negative 3. I would write it the other way around. Just negative 3 is less than x and x is less than negative 1. Right? Just draw it in the same direction, and those are equivalent. Right? These are actually the same inequality. Me personally, I just have a personal preference of having the smaller number on left and larger number on the right, right? So less than instead of greater than. Hopefully that made sense. All right. Now my last 3 examples, I'm just gonna do it out loud, or I just won't write out the steps that I'm doing. First, I would subtract 2, so I got negative 3 is less than 3x, and then 3x is less than 6, right? Subtracting 2 from all 3 parts. Then dividing all 3 parts by positive 3, so it keeps the direction of the inequality. That'd be negative 1 is less than x, and x is less than 2. So all the solutions of this compound inequality, everything that would make this a true statement, are values of x between negative 1 and positive 2. So there's a number line, there's negative 1, positive 2, and every number in between them, but not including them. So parentheses on those. And the interval notation, right, we're going from negative 1 to 2 here with parentheses on either end because neither one of those is a solution. All right, number 25 here. First I would subtract 2 from everything. So giving me negative 10 there, 5x in the middle, and 5x is less than or equal to negative 5, right? This again, subtracting 2 from all 3 parts. Then I would divide by positive 5. You have negative 2 is less than x, and x is less than or equal to negative 1. Now the variable's alone in the middle. I'm done. And we have a description of our solutions to this compound inequality, right? X is every number between negative 2 and negative 1, not including negative 2, but including negative 1. Negative 1 would be a solution here. Right. So here's negative 2, and it would be to the left of negative 1, right, on the number line. Everything in between, not including 2, but including 1. So parentheses on 2, brackets on negative 1. And the interval notation would be pretty simple. Again, everything from negative 2 to negative 1, not including negative 2, so parentheses there, and including negative 1, so bracket there. All right, and finally, one last example of one of these connected and inequalities, right? And as I mentioned before, only and inequalities, only where there's betweenness can you have a connected inequality like this. We'll see a video after this where we're talking about or inequalities, right? Inequalities connected by the word or. Inequalities connected by the word or can't be connected like this. It wouldn't make any sense. So please know that. All right, so first I would add 2 to all 3 parts. Negative 4 is less than or equal to 4x, and 4x is less than 0. All right, and then I would divide everything by positive 4, giving me negative 1 here is less than or equal to x, and x is less than 0. All right, dividing 0 by 4 is still 0. And there we go, the variables along in the middle. I am now describing all the solutions of this compound inequality. All the values that would make this a true statement are values of x between negative 1 and 0. Negative 1 is a solution, 0 is not. So between negative 1 and 0, everything between. Negative 1 is a solution, so bracket or closed point there. 0 is not a solution, so a parentheses or open point there. And then the interval notation for this picture, we're talking every number from negative 1 to 0, so negative 1 comma 0. Negative 1 is included, bracket, 0 is not included, parentheses. Wonderful. And that's it. All right, those were exercises from, again, section 2.6 of the openstacks.org Intermediate Algebra 2nd Edition textbook. It's a free online textbook. And those were exercises 376 through 401 of section 2.6. Right. Hopefully, again, I know it's the end of the video, but hopefully you're practicing these, before you watch me do them, and then watch me do them and see if you did everything correctly and all that. And hopefully watching these help you when you're working on similar problems in any other textbook. And thank you very much for watching.